In the beginning there was not light, but silence. A canvas stretched vast and unbroken, where darkness reigned without rival. Against this endless night, stars are no more than scattered sparks, fleeting lanterns adrift in an abyss without shore. Yet hidden within that abyss lies something greater than the brilliance of suns, an architecture vast beyond comprehension, unseen yet all-encompassing. The galaxies do not float at random. They cling to invisible strands, arranged like jewels along a web too immense to behold. It is not the stars that shape the universe, but something else, something older, something buried in silence. Astronomers now know that the cosmos we see, every shining star, every spiral arm, every blazing cluster, is only 5% of reality. The rest is hidden. This unseen order is called dark matter, a name not for what it is, but for what it refuses to be: light, energy, or substance that can be touched. It reveals itself only through gravity, the pull that bends galaxies into spirals and guides the birth of stars. Without it, the Milky Way would dissolve, clusters would scatter, the universe itself would fall apart. Dark matter is a paradox, a presence that cannot be touched, a framework without surface, a skeleton upon which all existence hangs. It is the structure hidden in eternal darkness, the silent architect of reality, and yet its essence remains unknown. Is it a particle unseen by the deepest detectors, a flaw in our understanding of gravity itself, or the shadow of higher dimensions folded just beyond reach? The mystery begins not with light, but with the dark, with the invisible structure that holds the stars. For most of human history, darkness was emptiness. The sky at night appeared as a dome sprinkled with stars, and what lay between them was believed to be void, a nothingness without form or structure. Ancient mythologies described the dark as chaos, a realm from which creation arose but which itself had no order. Light was substance, darkness was absence. The Babylonians recorded the motions of stars to foretell the future. The Egyptians tied the heavens to the cycles of the Nile. The Greeks wove geometry into the motions of planets, imagining crystalline spheres upon which celestial bodies were fixed. To them, the darkness carried no weight, no substance. The void was simply a backdrop for the eternal dance of stars. In Aristotle's philosophy, nature abhorred a vacuum. Emptiness was impossible. Space was always filled with something, even if unseen. Centuries later, Newton shattered the crystalline spheres and imagined an infinite stage, absolute space and absolute time, a perfect geometry upon which planets and stars obeyed gravity's pull. Still, the darkness was nothing more than background. Only matter mattered. For 2 centuries, Newton's cosmos endured. The motions of the moon, the paths of comets, the tides of Earth, all explained by visible matter and universal gravity. The stars burned, galaxies spun, but the rules were thought complete. The cosmos was clockwork, and in clockwork, nothing essential was missing. Yet, in the early 20th century, cracks began to form in this vision. In 1915, Einstein proposed that gravity was not a force, but the warping of space-time itself. Matter told space-time how to curve. Space-time told matter how to move. His equations described the motions of stars and galaxies with breathtaking precision, predicting phenomena never before seen. But buried within those equations lay hints that not all mass, not all energy, was visible. Relativity allowed for the possibility that unseen gravities might bend the universe. Still, no one expected that most of the universe would turn out to be invisible. The first true glimpse came not from Einstein, but from a Swiss astronomer with a reputation for bold claims. In 1933, Fritz Zwicky studied the Coma Cluster, a vast gathering of more than 1,000 galaxies drifting through space. By measuring the velocities of these galaxies, Zwicky realized they were moving too fast to be held together by the gravity of the matter seen within them. According to Newton's law, the cluster should fly apart, galaxies dispersing into the void. Yet it did not. Zwicky concluded that some hidden mass, dunkle materie, or dark matter, must exist, vastly outweighing the visible galaxies. It was the invisible glue binding the cluster together. His claim was revolutionary, and it was ignored. Zwicky was known for his bluntness, even hostility. Colleagues dismissed him as eccentric, perhaps exaggerating his results. For decades, the notion of unseen matter slumbered in obscurity. Astronomers returned to their telescopes, charting galaxies, stars, and clusters with no thought that reality might be built upon an invisible skeleton. The breakthrough would not come until the 1970s. Vera Rubin, working with Kent Ford, turned their attention to the Andromeda Galaxy and others beyond. Using precise spectrographs, they measured how stars at different distances from the galactic center orbited their cores. By Newtonian expectation, the rotation curve of a galaxy should behave like the solar system, inner stars orbiting quickly, outer stars moving more slowly as gravity weakens with distance. But Rubin and Ford discovered something astonishing. The stars far from the center moved just as quickly as those near the core. The rotation curves were flat, refusing to decline. It was as though a vast halo of unseen mass enveloped each galaxy, extending far beyond the luminous spiral arms. This was no anomaly. One galaxy after another revealed the same strange pattern. The stars were racing upon invisible scaffolding, bound by gravity not of light, but of shadow. The skepticism that had haunted Zwicky could no longer stand Rubin. Meticulous data made denial impossible. The cosmos was veined with matter unseen. Darkness was not emptiness. It was structured by the late 20th century. The evidence mounted from all directions. Galaxy clusters once again revealed missing mass. X-ray observations showed hot gas that should have evaporated without additional gravitational binding. Einstein's own prediction of gravitational lensing, the bending of light by mass, revealed arcs of distant galaxies stretched and distorted, not by visible matter, but by invisible gravities. The luminous universe was being redrawn. What humans once believed was the main story, stars, nebulae, galaxies, was revealed to be only a thin crust, a fragile frosting upon an invisible cake. The cosmos had a hidden skeleton, unseen yet essential, in the laboratories of cosmology. The shift was profound. The equations of astrophysics now required an additional ingredient. Without dark matter, the models failed. With it, galaxies formed, clusters bound together, and the universe unfolded as observed. The discovery was humbling. For millennia, humanity had gazed into the night sky, believing the stars revealed the true cosmos. Now, astronomers realized they had been watching only shadows on the surface of something vaster, something hidden in eternal darkness. Zwicky's whisper had become Rubin's proof, and Rubin's proof had become the foundation of modern cosmology. The visible universe was no longer the main story, but the exception. The question, however, remained, what was this invisible mass? If it was not stars, not gas, not dust, then what? The discovery phase ended not with answers, but with a greater mystery. The cosmos was built upon darkness, and no one knew what the darkness was made of. For the first time, astronomers stood not in front of an eternal, luminous sky, but at the threshold of an unseen realm, one that silently guided galaxies and perhaps destiny itself. The age of dark matter had begun. The shock did not come all at once. It came slowly, like the creeping realization that the ground beneath one's feet is not solid, but fragile, a thin crust above an abyss. For centuries, astronomy had been a science of light. Telescopes gathered photons, tracing them back to stars, galaxies, and nebulae. The cosmos was what shone. And yet, by the late 20th century, the evidence could no longer be ignored. The luminous sky was not the whole of reality. It was, at best, 5% of it. The shock began with rotation curves. In galaxy after galaxy, stars far from the center spun at impossible speeds. By all Newtonian expectation, the velocity should drop with distance, just as the outer planets of the solar system move more slowly than the inner ones. But the galaxies defied the rule. Their stars moved as though cradled in vast halos of invisible mass. This was not a marginal anomaly. It was universal. Spiral galaxies, elliptical galaxies, dwarf galaxies, all bore the same flat curves. To deny the pattern would be to deny the data itself. The laws of gravity still held, but they pointed to something unseen. The realization was unsettling. The familiar was not fundamental. The stars, the nebulae, the bright heart of the Milky Way, all were bound not by what they revealed, but by what they concealed. Clusters of galaxies deepened the mystery. Astronomers measured the motions of galaxies inside them and compared the results with the amount of visible matter present. Once again, the speeds were too high. Without additional mass, the clusters should have flown apart long ago. Hot gas, glowing in X-ray telescopes, filled the void between galaxies. Yet even this gas was insufficient to account for the binding force. Something invisible held them together. Then came the lensing. Einstein's general relativity had predicted that light itself would bend when it passed near massive objects, curving space into a lens. In 1919, during a solar eclipse, starlight had been observed bending around the sun, confirming Einstein's vision. But in the late 20th century, astronomers began noticing distortions not explained by visible galaxies. Arcs of light from distant galaxies stretched and curved as though molded by gravitational hands that could not be seen. The phenomenon became undeniable with the Bullet cluster in 2006. Two galaxy clusters collided in a cosmic crash. The ordinary matter, gas, and plasma slammed together, slowed and heated. But the gravitational lensing revealed that the true mass had passed through untouched, moving ahead of the visible wreckage. Dark matter, immune to collisions, had revealed itself not by being seen, but by separating from light entirely. The shock was total. The cosmos was not defined by what could be observed, but by what remained hidden. The galaxies were lanterns strung along unseen threads, glowing beads upon a web of shadow. For physicists, the implications cut deeper still. If the majority of matter in the universe was invisible, then the standard model of particle physics, the proudest achievement of 20th century science, was incomplete. None of its known particles could account for the missing mass. Neither electrons nor protons, neither photons nor neutrinos, carried the right properties. Something else, something outside the known framework, had to exist. The contradiction pierced the heart of physics. The Standard Model had triumphed in predicting the Higgs boson, in unifying the electromagnetic and weak forces, in explaining the zoo of subatomic particles with astonishing accuracy. Yet here was the universe itself, declaring that most of its mass lay beyond that model's reach. This was more than a puzzle. It was a revolution waiting to be born. For astronomers, the emotional weight was profound. The night sky, once thought to be a map of all that exists, was suddenly revealed as a mirage. The stars traced only the outlines of an invisible framework. The galaxies glowed, but they were not the foundation. The true cosmos was hidden, a shadow realm silently shaping everything, and with this revelation came dread. If the cosmos was mostly unseen, how much of reality lay forever beyond comprehension? If the visible was only the surface, what depths of existence might remain unknown? The numbers were merciless. Only about 5% of the universe was the matter of atoms, everything that burns, reflects, or glows. About 27% was dark matter, unseen yet gravitationally essential. And the remaining 68%, stranger still, was something even less understood. Dark energy, a force not of binding, but of expansion. It was the ultimate inversion. What had been assumed to be the main story, stars, planets, nebulae, was relegated to a cosmic footnote. The true tale was written in shadow and silence. The shock resonated across philosophy as well as physics. Humanity had always equated light with knowledge, darkness with ignorance. To know was to bring into the light. But here, the universe itself suggested that darkness was not ignorance, but substance. The unseen was not absence. It was the foundation, and in that foundation lay another paradox. If dark matter had been slightly weaker, galaxies would never have formed. The universe would have expanded into emptiness, stars never born. If it had been stronger, the cosmos might have collapsed upon itself too quickly for life to arise. The hidden matter seemed tuned with exquisite precision, allowing galaxies to emerge, stars to ignite, and eventually, life to wonder at its own origins. The realization was as humbling as it was terrifying. Humanity was not built upon light, but upon shadow. Existence itself was cradled by an invisible skeleton, one that revealed itself only through its pull on the visible. The scientific shock was complete. The laws of physics had not failed, they had pointed beyond themselves. The discovery of dark matter was not just a new chapter in science. It was the recognition that the cosmos is stranger than imagination, and that reality itself hides more than it reveals. Darkness was no longer absence. It was the structure of the universe. The shock of discovery left astronomers with a new and unsettling mandate: to look for what could not be seen. If galaxies were strung like beads upon invisible threads, then those threads must be mapped. If gravity was sculpting light through hidden hands, then the hands themselves must be traced. The task was monumental, to reveal a structure that revealed itself only through absence. By the late 20th century, scientists turned to simulations, building digital universes within the memory of supercomputers. They began by seeding these universes with only the visible matter of stars and gas. The result was lifeless. No galaxies formed. No clusters emerged. The luminous matter dispersed into a diffuse haze, unable to clump together strongly enough to forge stars. Then they added dark matter. Immediately, structure appeared. Invisible halos grew dense, pulling in gas, guiding it into filaments. Within these dark skeletons, galaxies lit up like lanterns along roads. Clusters swelled at intersections where filaments met. For the first time, astronomers saw how dark matter was not just scaffolding, but architect. Without it, there was no cosmos as we know it. The cosmic web was born in silico before it was revealed in the sky. Soon, telescopes confirmed its reality. Redshift surveys, like the Sloan Digital Sky Survey, mapped millions of galaxies, revealing patterns that stretched across hundreds of millions of light years. The universe was not random scatter, but tapestry, vast filaments and empty voids, a structure more akin to foam or lace than to the chaos once imagined. But how to trace what lay beneath the light? Astronomers turned to gravitational lensing, not the strong arcs seen in clusters, but the subtler distortions of weak lensing, the minute stretching of background galaxies as their light passed through invisible mass. By stacking thousands of these distortions, they mapped dark matter directly. Slowly, the hidden skeleton emerged, vast tendrils binding clusters, shadows etched into space-time itself. Then came the bullet cluster, the most dramatic revelation of all. Two massive clusters of galaxies, each containing trillions of stars, had collided in a cataclysmic crash. The visible matter, mostly hot gas, slammed together, slowed by friction, and glowed in X-rays. But the gravitational lensing told another story. The true mass had passed straight through, unaffected, continuing beyond the crash. The visible and invisible had parted ways, and in their separation, the dark matter revealed itself with undeniable clarity. The bullet cluster became the Rosetta Stone of cosmology. It showed that dark matter was not an illusion of misunderstood gravity, but a distinct, collisionless substance. It interacted through gravity, but not through light or friction. It was there, ghost-like, weaving through the wreckage of galaxies. While astronomers mapped its presence, physicists turned inward to the subatomic realm. If dark matter shaped galaxies, then what was it made of? The Standard Model offered no answer. New candidates arose. The first were WIMPs, weakly interacting massive particles. Heavy, stable, born in the furnace of the Big Bang. They were thought to linger still, drifting silently through every cubic centimeter of space, through every human body, through Earth itself, unnoticed. Theoretical calculations showed that, if such particles had existed, their relic abundance would match the dark matter needed. It seemed too perfect to be coincidence. Experiments were built to catch them. In mines deep underground, shielded from cosmic rays, vats of liquid xenon and germanium crystals sat waiting for a rare collision between dark matter and an atomic nucleus. For decades, detectors listened to the silence, each flicker of energy, scrutinized for signs of the invisible. The searches narrowed possibilities, but no detection came. Other candidates arose, ixions, hypothetical particles born to explain why the strong nuclear force obeys certain symmetries. If they exist, they would be unimaginably light, but collectively abundant, forming halos of dark matter around galaxies. To detect them, scientists built resonant cavities and magnetic traps, instruments designed to tune into the faint whispers of axion waves. There were sterile neutrinos, ghostly cousins of known neutrinos, interacting only through gravity. Primordial black holes, relics of the infant universe, too small to shine, too abundant to see. Dark photons, mirror particles, mediating forces in a hidden sector of physics. Each candidate was speculative, yet each pointed to a possible key to the skeleton of the cosmos. The investigation spread to the oldest light in the universe, the cosmic microwave background, discovered in 1965 by Penzias and Wilson, became a treasure map of hidden structure. Satellites like COBE, WMAP, and Planck traced its tiny fluctuations. Ripples in temperature and density imprinted when the universe was only 380,000 years old. The patterns revealed how matter, both visible and dark, had clumped under gravity. The ratio was precise, about 27% dark matter, 5% ordinary matter. The CMB became a silent witness to the invisible. It confirmed that dark matter was essential from the very beginning, guiding the collapse of gas into the first stars, setting the stage for galaxies long before the cosmos glowed with light. And yet, mysteries deepened. Simulations with dark matter predicted vast numbers of small galaxies orbiting larger ones, but in reality, far fewer were seen. The missing satellites problem suggested either that dark matter behaved differently than expected, or that small galaxies had been stripped and destroyed. Some dwarf galaxies, curiously, seemed to contain little or no dark matter at all, defying expectation. Others appeared dominated by it almost entirely. On smaller scales, the skeleton seemed inconsistent, as though the dark matter might be self-interacting, colliding subtly with itself, or possessing properties still unimagined. The investigation had grown into a labyrinth. The cosmic web confirmed dark matter's grip. Lensing revealed its filaments. Collisions showed its independence from ordinary matter. The microwave background confirmed its ancient role. Particle physics offered candidates, but none yet captured, and so the paradox deepened. The hidden structure was everywhere, shaping everything, yet refusing to reveal its nature. Humanity had mapped the bones of the universe, but not its flesh. The skeleton was etched across billions of light years, but what it was made of remained. An unanswered riddle. It was not ignorance alone. It was a boundary of knowledge, a horizon between what could be measured and what could only be imagined. The deeper the investigation went, the more the darkness resisted. The deeper the search went, the more elusive the hidden structure became. Every discovery was paired with contradiction, every certainty shadowed by doubt. What was once thought to be a straightforward hunt for an unseen particle grew into one of the most profound enigmas in all of science. The cosmos had revealed its skeleton, but not its substance. And as astronomers pressed further, the mystery only deepened. Decades of underground experiments had listened to the silence. WIMPs, once the favored candidate, slipped through the nets of detectors. The Large Hadron Collider, the Great Cathedral of particle physics, smashed protons with unprecedented energy, searching for supersymmetric partners that might carry the weight of dark matter. None appeared. Each non-detection was not just a disappointment, but a reconfiguration of hope. The universe seemed to say, "Look deeper or look elsewhere." This silence sowed doubt. Perhaps dark matter did not exist at all. Perhaps the cosmos was governed by laws more subtle than Newton or Einstein had imagined. A rival idea stirred, that gravity itself might require rewriting. Modified Newtonian dynamics, or MOND, suggested that at extremely low accelerations, the force of gravity behaves differently than expected. On galactic scales, MOND could reproduce the flat rotation curves without invoking invisible matter. Later, more sophisticated extensions like TeVs sought to reconcile such modifications with relativity. These theories were bold, elegant, and deeply controversial. They did not solve every puzzle, yet they lingered as whispers of defiance against the prevailing orthodoxy. the mystery fractured further at small scales. Simulations predicted an abundance of dwarf galaxies swarming around the Milky Way like fireflies, yet only a handful were found. Where had the others gone? Some astronomers proposed that they had been stripped away by cosmic tides, torn apart before discovery. Others suspected that the simulations were wrong, that dark matter might interact with itself or with baryons in ways never considered. Then came galaxies that defied expectation altogether. In 2018, researchers announced the discovery of a galaxy, NGC 1052 DF2, seemingly devoid of dark matter. Its stars and gas alone explained its motion. If confirmed, this meant that galaxies could exist without the skeleton, challenging the notion that dark matter was a universal foundation. Later, another galaxy, DF4, appeared to share the same peculiarity. Some argued the measurements were flawed, or that tidal interactions had stripped away the invisible halo. But the possibility remained unsettling. Perhaps dark matter was not evenly distributed, but capricious, complex. Other galaxies appeared the opposite, dominated almost entirely by dark matter, with stars as sparse lanterns adrift in enormous, invisible halos. This inconsistency made the hidden structure seem less like a universal law and more like a chaotic riddle. On the larger scales, dark matter held steady, sculpting the web, but on the intimate scales of galaxies and clusters, cracks appeared. The skeleton was both undeniable and contradictory, steadfast and evasive. In 2006, the bullet cluster delivered clarity, but it also sharpened the paradox. The separation of visible and invisible mass demonstrated dark matter's independence. Yet similar collisions did not always yield the same clean results. Some merging clusters hinted at behavior inconsistent with cold, collisionless particles. Perhaps dark matter was not passive, but self-interacting, exchanging momentum in hidden ways. Each observation added nuance, each hypothesis splintered the mystery further, and above it all, the cosmos itself complicated the picture. Observations of the cosmic microwave background painted one portrait of the universe's expansion rate. Measurements of nearby galaxies painted another. This Hubble tension hinted that something fundamental was missing, perhaps tied not to dark energy, but to the properties of dark matter itself. The unknown expanded like the universe it described. The hidden skeleton was not a singular enigma, but a landscape of uncertainty, branching into countless possibilities. Speculations grew more audacious. Some physicists proposed dark sectors, entire families of particles and forces existing alongside ours, interacting only through gravity. In such a universe, dark matter might not be a single particle at all, but a shadow cosmos with its own physics, invisible yet parallel, shaping ours in silence. Others turned to primordial black holes, relics of the infant universe. If dense regions collapsed just after the Big Bang, they could form black holes of many sizes, too small to be seen, yet numerous enough to account for the hidden mass. Gravitational wave observatories began testing this idea, listening for mergers of black holes that might reveal their primordial origin, and still the skeleton remained mute. The escalation was not only scientific, but philosophical. Humanity had grown accustomed to the idea that the universe could be explained, that equations could pierce every veil. Yet here was a structure more dominant than stars, more ancient than galaxies, and it refused to yield. The cosmos had handed astronomers a paradox. The universe was shaped by what could not be seen, by what might never be touched. The unease deepened. If the skeleton was real, it defined existence itself. If it was an illusion, then the very laws of gravity were incomplete. Either path led to a rewriting of reality. The hidden structure did not shrink with scrutiny. It grew, multiplying horizons of ignorance. Each telescope, each detector, each simulation revealed more of its outline, but none of its essence. The darkness had become not emptiness, but a mirror of limitation. And in this mirror, astronomers saw themselves fragile beings, mapping a cosmos held together by shadows. They had charted filaments spanning billions of light years, traced invisible mass through collisions of clusters, measured its fingerprints in the oldest light. Yet the question remained untouched. What is it? The escalation was not a narrowing of answers, but an expansion of possibilities. A reminder that the cosmos is larger than the tools of knowledge, and that the greatest structures may forever resist the grasp of certainty. The skeleton was undeniable, but the darkness was still eternal. The scaffolding of the universe was undeniable. Galaxies spun too quickly, clusters clung too tightly, light bent too sharply. Something unseen was shaping the cosmos. But if observation defined its outline, theory sought its substance. And here, in the most shadowed corridors of science, speculation bloomed like stars in the dark. The first contender, and for decades the favorite, was the WIMP, the weakly interacting massive particle. Born of extensions to the Standard Model, WIMP were imagined as heavy, sluggish particles, relics of the hot early universe. Their great appeal lay in coincidence. If they existed, their predicted abundance matched the amount of dark matter required by observation. It was a cosmic riddle seemingly solved by elegance. Yet silence answered the detectors. Underground, caverns filled with noble gases waited for the faint recoil of a WIMP colliding with an atom. Years passed, sensitivity deepened, but no trace appeared. With each null result, the once bright promise of WIMPs dimmed. Attention turned to subtler candidates. The axion, a featherweight particle conceived to solve a problem in quantum chromodynamics, offered another possibility. Unlike WIMPs, would be nearly massless, but abundant enough to form vast halos of invisible matter. They might even coalesce into exotic states of axion stars, subtle fogs of darkness floating between galaxies. Experiments began listening for their faint transformation into photons within magnetic fields. As of yet, no whisper has been heard, but the hunt continues. Another shadowed suspect emerged, the sterile neutrino. Ordinary neutrinos, already ghost-like, stream through matter almost unimpeded, but a sterile cousin, interacting only through gravity, could provide the mass needed to shape galaxies. Unlike WIMPs or ixions, sterile neutrinos would not be entirely new in concept, but a hidden extension of a known particle. X-ray telescopes scanned the skies for faint decay signals that might betray their presence. Some hints flickered at the edge of detection, though never strong enough to confirm. Beyond particles, speculation widened to the primordial. Perhaps the hidden mass was not made of particles at all, but of black holes, forged in the violent infancy of the cosmos. If the early universe contained fluctuations of extreme density, they might have collapsed into black holes long before stars formed. These primordial black holes would roam unseen, massive enough to hold galaxies, yet dark enough to masquerade as invisible matter. Gravitational wave detectors began to probe this possibility, listening to the collisions of black holes for signatures that might hint at primordial origins. For now, the evidence is inconclusive, but the possibility lingers. Some physicists cast their nets even wider, proposing dark sectors, hidden families of particles and forces parallel to our own. In this vision, dark matter is not a single particle, but a shadow cosmos, governed by its own interactions, invisible except for gravity. Just as ordinary matter forms atoms, stars, and galaxies, so too might the dark sector weave its own structures, unseen yet fundamental. The thought is unsettling, a mirror universe entwined with ours, silent but inexorable. And then there are those who question the very need for particles. If the cosmos refuses to yield dark matter's identity, perhaps the fault lies not in the unseen, but in the equations themselves. Modified Newtonian dynamics, Mond dared to challenge gravity itself. Instead of unseen matter, Mond proposed a shift. At extremely low accelerations, gravity acts more strongly than expected. On galactic scales, this adjustment explained flat rotation curves with surprising accuracy. Later refinements, like Teves, extended the idea to a relativistic framework. Yet these theories falter on cluster and cosmic scales, where unseen mass still seems necessary. They remain controversial, a heresy to many, but a reminder that even gravity, the oldest of forces, may not yet be fully understood. Speculation grows, stranger still. Some imagine dark matter as dark photons, echoes of light tied to hidden fields. Others see it as mirror matter, an exact duplicate of the standard model, reflecting our own physics into a hidden dimension. Still others tie it to the vast frameworks of string theory, where countless possible universes each possess their own vacua, their own hidden particles. In this view, dark matter may not be a puzzle to be solved, but a natural feature of a multiverse. Landscape, one possibility among endless variations. Yet each theory carries both promise and peril. WIMPs remain elegant, but undetected. Ixions solve deep quantum puzzles, but remain whispers in silence. Sterile neutrinos hint through shadows, but never with clarity. Primordial black holes tempt with gravity's allure, yet remain elusive. Modified gravity explains some scales, but fails on others. The dark sector tantalizes, but stretches imagination toward the metaphysical. The deeper truth may be that dark matter is not singular. The cosmos, with its layers of complexity, may hide more than one kind of invisible mass. Just as ordinary matter divides into protons, neutrons, electrons, and beyond, so too might the dark consist of families, each playing its role in the grand. Architecture. This multiplicity reflects the philosophical tension at the heart of the mystery. For centuries, science has thrived on the assumption that the universe can be explained with clarity, that hidden forces yield under scrutiny. But here lies a paradox. The very structure that makes existence possible refuses to show its face. The skeleton of the cosmos may be forever obscured, not by chance, but by nature. And so, speculation becomes more than science. It becomes a meditation on knowledge itself. Is dark matter a particle awaiting discovery, or is it a sign that the laws we worship are incomplete? Is it a reminder that human understanding, like starlight, can only travel so far before fading into shadow? Each theory, from WIMPs to Mond, is not only an attempt to solve the cosmic riddle, but a reflection of humanity's refusal to accept ignorance. In the laboratories deep beneath mountains, in the detectors listening for whispers, in the supercomputers simulating galaxies, humanity confronts the most humbling truth. The universe is built on what cannot be seen. Speculation does not close the mystery. It enlarges it, wrapping the cosmos in deeper shadow. Yet within that shadow glimmers awe that the visible universe, fragile and radiant, is upheld by something vaster still. Theories may rise and fall, experiments may confirm or deny, but the structure hidden in eternal darkness remains. Whether it is particle, field, or flaw in the laws themselves, it stands as a silent cathedral of ignorance and wonder. And in this cathedral, humanity kneels not in despair, but in reverence. The dark does not yield answers easily, but perhaps that is its gift, to remind that mystery is not absence, but presence, that ignorance is not failure, but invitation, and that within eternal darkness lies not emptiness, but the possibility of endless discovery. To chase the invisible is to attempt the impossible. Yet for nearly a century, astronomers and physicists have constructed machines not to see dark matter directly, but to glimpse its influence, its echoes, its fingerprints left upon the cosmos. Each tool is a lantern held against the eternal night, fragile, human-made, yet daring to reveal the unseen skeleton of existence. The most direct attempts lie hidden deep beneath the earth, in caverns shielded from cosmic rays. Detectors wait for worse spurs. Xenon, buried beneath Italy's Gran Sasso Mountains, holds vats of liquid xenon, chilled to near absolute zero. There, scientists hope that a passing particle of dark matter might collide with a xenon nucleus, creating a faint flash of light and a ripple of electrons. For decades, these detectors have grown larger and more sensitive. First XENON10, then XENON100, then XENON1T, now Xenont and its competitors like Luxaplin in South Dakota and Pandarex in China. Each expansion carries the same hope that one day the silent storm of dark matter streaming through the earth will betray itself with a single, unambiguous signal. Yet silence persists. The detectors grow quieter, their patience deeper. The dark remains unbroken. If direct collisions cannot yet be captured, then perhaps dark matter reveals itself in annihilation. Indirect detection turns telescopes skyward, searching for the debris of invisible interactions. If dark matter particles meet, they might annihilate, releasing gamma rays, neutrinos, or other particles of light. The Fermi Gamma Ray Space Telescope has scanned the galactic center, hoping to find excess photons betraying such events. Subtle hints appear, debated fiercely, then fade into uncertainty. Neutrino detectors, like IceCube, buried in Antarctic ice, listen for elusive signals of annihilation. No clear voice yet speaks from the dark. High above, particle colliders, like the Large Hadron Collider LHC at CERN, smash protons together at energies approaching those of the early universe. Here, physicists seek to create dark matter itself, particles too shy to linger, slipping unseen from the collisions, leaving only missing energy in their wake. For years, hopes rode high that supersymmetric particles might emerge, neatly explaining dark matter's mystery. But as the collider's data expanded, no such shadows appeared. Still, the collisions continue, because every absence narrows the possibilities, and every silence sculpts the boundaries of truth. If colliders and detectors probe the microcosm, telescopes turn outward, painting the macrocosm. The Vericy-Rubin Observatory, soon to begin its grand survey, will map billions of galaxies across the sky, tracing their distribution with unprecedented precision. From these patterns, the pull of dark matter may be inferred, as if revealing the brushstrokes of an invisible painter. Its lens will not see the particles themselves, but the architecture they shape. Alongside Rubin, space telescopes take their place in the hunt. The Euclid mission of the European Space Agency launched to chart dark energy and dark matter alike, mapping the subtle distortions of light caused by gravitational lensing. The Nancy Grace Roman Space Telescope, NASA's own dark energy hunter, will soon join the quest. Together, these observatories will peer deeper into cosmic scaffolding, capturing the contours of invisible filaments stretching across billions of light years. The evidence grows sharper in collisions beyond the laboratory, collisions of galaxies themselves. When clusters crash, ordinary matter slows and heats, but dark matter, immune to friction, sails onward. Observations of the bullet cluster and later of similar collisions provided perhaps the clearest proof of dark matter's independence. New telescopes continue to watch such cosmic wreckage, refining maps of mass distribution, tracing the skeleton with finer strokes. Still, the enigma deepens. If dark matter were primordial black holes, then gravitational wave astronomy may hold. The key, LIGO, Virgo, and Cagra already record the mergers of stellar mass black holes, sending tremors across space-time. Future instruments like LISA, a gravitational wave observatory in space, may detect mergers on cosmic scales, potentially, distinguishing between black holes born from stars and those born from the earliest moments of the universe. Should primordial black holes exist, their signature may one day resonate through space-time itself at the largest scale. The cosmic microwave background remains one of the most powerful tools. The Planck satellite measured with exquisite detail the faint afterglow of the Big Bang, revealing not only the total amount of dark matter, but its role in shaping early fluctuations. Yet mysteries remain. Upcoming missions, like Light Bayard and CMBs-4, will attempt to refine this map still further, searching for signatures of inflation and subtle deviations that might hint at the nature of the dark. Meanwhile, simulations attempt to bridge theory and observation. With supercomputers running trillions of calculations, scientists model universes with and without dark matter, comparing the results to the cosmic web revealed by telescopes. These simulations show how dark matter halos cradle galaxies, how filaments connect clusters, how voids expand into vast cosmic deserts. They are not answers, but rehearsals for the unseen symphony that shapes the stars. Even laboratories join the cosmic stage in stranger ways. Physicists create ultra-cold atomic clouds, Bose-Einstein condensates, to simulate conditions of dark matter fields. These analog experiments echo cosmic phenomena at miniature scales, offering new ways to test the properties of ixions or hidden forces. In this way, the laboratory becomes a microcosm of the universe itself. What emerges is not certainty, but a constellation of approaches. Each tool, the underground detectors, the colliders, the telescopes, the gravitational wave observatories, the simulations is a different sense extended into the dark. Alone, none can solve the riddle. Together, they weave a net, tightening around the unknown, drawing humanity closer to revelation. And yet, the most haunting possibility remains, that dark matter may never yield fully to detection. Perhaps it lies forever beyond the grasp of instruments designed for visible matter. Perhaps its substance belongs to realms inaccessible to light, to energy, even to thought. If so, then these tools are not failures, but testimonies, records of humanity's refusal to surrender before mystery. The effort itself becomes symbolic. To weigh the weightless, to see the unseen, to map the skeleton of reality, is to declare that ignorance is not defeat but challenge. Science does not abandon the dark. It steps into it, armed with patience, imagination, and instruments that extend the reach of human senses across billions of years and trillions of miles, every flash in a detector, every ripple in space-time, every distortion of light is a message from the invisible. Each tool may fail alone, but together they whisper a story that beneath the radiance of stars lies a greater shadow, and within that shadow, the truth of existence itself. The story returns to where it began, the stars scattered like fragile embers in an ocean of night. For millennia, humanity believed that light was the truth of the cosmos, that what was seen was what was real. Yet the revelations of modern astronomy have turned this intuition inside out. The deeper the universe is measured, the clearer the paradox becomes. Light is not the foundation, but only its adornment. Beneath every shining star lies a hidden architecture, a structure that does not glow, yet defines the shape of everything that does. This is the haunting lesson of dark matter. It is not a faint detail at the edges of science, but the very skeleton of existence. Without it, galaxies would disperse, stars would never ignite, and the cosmos would be formless, adrift in chaos. The visible world, planets, suns, life, thought rests upon an unseen lattice, as fragile lace rests upon invisible threads. Darkness, long feared as absence, is revealed as the condition for presence, and yet its nature remains unknown. For nearly a century, physicists have hunted the substance of this shadow. They have built machines buried beneath mountains, telescopes orbiting Earth, and simulations that span billions of years. They have imagined particles, fields, hidden sectors, and dimensions. None have yet yielded the final answer. The structure remains hidden, not in absence, but in silence. This silence provokes reflection. Perhaps the universe is not designed to yield all of its secrets. Perhaps there are layers of reality that resist translation into human mathematics. Or perhaps the mystery is temporary, awaiting an idea not yet born, a theory not yet written. History reminds us that once atoms were invisible, gravity inexplicable, and the very expansion of the cosmos inconceivable. To live in mystery is not defeat, but the ordinary condition of knowledge. There is something profoundly human in this pursuit. The visible sky inspires awe, but it is the invisible that compels humility. To know that the stars rest upon a shadow that no eye has ever seen is to recognize the limits of perception. In this recognition lies philosophy. Reality is not what it seems. The human mind navigates not the universe as it is, but the fraction it can perceive. Dark matter is a mirror, reflecting both the immensity of the cosmos and the smallness of human comprehension. Yet in that smallness is beauty. The very fact that humanity can infer the existence of dark matter from the motion of galaxies, from the bending of light, from the resonance of cosmic radiation, is itself astonishing. Against the backdrop of a universe ruled by silence, the human species has listened carefully enough to detect the unspoken. The skeleton remains hidden, but its outline has been traced by persistence and imagination. Philosophers once spoke of shadows on the wall of Plato's cave, images mistaken for reality. In a sense, astronomy today confirms this metaphor. The luminous galaxies are shadows, projected upon the scaffolding of the unseen. The light we cherish, the nebulae we photograph, the stars we measure, are only tracings upon a structure invisible yet essential. The cave wall is the night sky, and the fire behind it burns in eternal darkness. What, then, does this mean for humanity? It means that existence itself is precarious, resting on laws and substances we do not yet comprehend. Life is not a triumph of clarity, but a flowering upon hidden roots. To live is to dwell in mystery. To think is to lean upon foundations unseen. The search for dark matter is not only scientific, it is existential. It reminds us that truth is larger than sight, larger than certainty, larger than the momentary. Confidence of equations there is, too, a lesson about humility. For centuries, humanity has placed itself at the center, first of Earth, then of the sun, then of the galaxy. Each step outward brought disillusion, but also a deeper belonging. Now comes the greatest displacement of all, the recognition that reality itself is dominated not by what shines, but by what does not. The cosmos is not primarily a theater of light, but a cathedral of shadows. Humanity exists not in spite of this darkness, but because of it. And so, the image returns, galaxies floating like lanterns upon invisible filaments. Each light is delicate, yet together they sketch a web across eternity. Within that web lie stars, planets, oceans, consciousness, all contingent, all temporary, all real because of what cannot be seen. The structure hidden in eternal darkness is not only a scientific riddle, it is a parable about existence. What is unseen sustains what is seen. What is silent sustains what can speak. The future remains open. Perhaps one day a particle will flash within a detector, undeniable and precise. Perhaps a new equation will dissolve the mystery into comprehension. Or perhaps the silence will remain eternal, a reminder that the universe is deeper than human logic. In either case, the pursuit itself carries meaning. To seek the unseen is to affirm that mystery is not a wall, but a horizon. For the astronomers who map the sky, for the physicists who wait in dark laboratories, for the thinkers who imagine hidden dimensions, the work is more than technical. It is spiritual in its own way. To probe the darkness is to ask what it means to exist in a reality where light is not the foundation. To live in such a universe is to be humbled, but also ennobled, for if humanity can glimpse even the outline of the invisible skeleton, then it has already crossed a threshold. It has already woven meaning from silence. The closing image is haunting and serene, the night sky above earth, its stars scattered like sparks across blackness. The eye sees light, but the mind now knows that beneath it lies darkness, more vast, more powerful, more enduring than any star. It is this darkness that binds galaxies, that nurtures the fragile flame of life, that holds reality together. It is eternal, yet hidden, silent, yet decisive. And so the final meditation arises. Perhaps the universe is not built upon light, but upon shadow. Perhaps what is unseen is more real than what is seen. Perhaps the eternal darkness is not absence but foundation, the hidden structure upon which everything rests. In this truth lies both terror and beauty. Terror, because it reminds us of ignorance, of fragility, of dependence on what cannot yet be named. Beauty, because it reveals a universe deeper than vision, richer than certainty, more mysterious than comprehension. To live within such a cosmos is not to despair, but to marvel. The story ends, but the question does not. The structure hidden in eternal darkness remains patient, silent, immense. Humanity stands beneath it, fragile yet aware, luminous yet dependent, fleeting yet searching. To know the darkness is to glimpse the foundation of all things. To accept the mystery is to live within wonder. The stars may fade, galaxies may scatter, civilizations may pass, but the skeleton endures. And within that endurance lies meaning, that the universe is larger than light, larger than time, larger than all that can be spoken. The hidden darkness holds us, and in its silence it whispers the eternal truth of existence.